Come on, Zoom. Come on, Zoom. Oh, there we go. I think we're streaming. Sorry about that. My bad. Looking at the wrong thing. All right. So we're live streaming now. Tonight, our goal is to talk about moment of inertia. And rather than start with a bunch of math, let's start by looking at some stuff, some actual physical objects. So I thought maybe this might be a fun way to start. Oops. Oh boy, I really got this lit on here. There we go. Probably seen something like this before in your life. It's a metronome, right? And so I'll just show you some different things here. This actually is a good summary of why we might care about all of this stuff. So you can see this is a large mass here. I don't know if I point this sideways. This is a thin rod. It has negligible mass compared to this thing and that thing right there, this little doohickey. And the idea is this can slide up and down. All right. So I don't know if you can hear that, but when the mass is located at this position, it oscillates at a certain rate. When I go up here, it's much slower. And if I go very close to the axis, you could really hear this thing going quickly. The whole point here is when I change the location of the mass, sorry, I'm just buckling this thing down again so it doesn't make noise on me. If I change the location of this mass relative to this pivot point, the moment of inertia changes, which affects how quickly this thing moves back and forth. So if we want to understand something as simple as this pendulum, we need to understand, well, first off, rods and point masses. So another way we might look at this, oops, here's kind of a blow up of this. And let me bring my white backboard here so you can see a little better. That is not where we want to start. Okay, say we have this thing right now, and I'll bring it a little bit closer. You can see that there's a screw right there. So I'm holding the backside of this thing like that. I'm just holding the screw, okay? So that is the pivot point right here. And the idea is I can make this thing swivel here. Now, normally I would mount this to some device that you've seen many times, but it's just a little bit easier for me to have it unbolted today so I can kind of show it and move it around. The idea is this is very similar to that metronome if I view it like this, right? If I adjust the location of one of the point masses, whoops, it's pretty hard for me to hold this and not screw it up. But it oscillates faster down with this mass here than if it does. Whoa. Oh my gosh. Yeah, so it's a little top heavy now. There we go. But yeah, now it's a very slow oscillation. So another way to think about this is like a figure skater spinning around in a circle. If they have their arms out, now you can't even, if you have your arms out, you have a large rotational mass. You have a large moment of inertia. The axis in that case is an imaginary line going through your body all the way down to the floor. And so there, if your arms are out, you'll tend to rotate slowly. Whereas if you bring your arms in, you can rotate more rapidly. We'll talk about that more in chapter 11 when we talk about angular momentum. But that's essentially the same thing as this. Now it's a lot more complicated because a human being is not a rod with negligible mass and two pieces of brass, but it's the same effect of taking mass far from the axis versus mass close to the axis. And so our goal is to not only conceptually understand that, but also know the idiosyncrasies of calculating moments of inertia. And if we can't calculate moment of inertia, the rest of the semester is brutal. Whereas if you learn a few tricks, it's totally doable. I'm not going to lie to you. It's challenging at first. It seems almost mysterious why I'll do one problem one way and another problem another way. Well, I'm going to try to go to great lengths to make sure you understand the subtleties of why I do this problem this way, that problem that way. So let's now go to the workbook, page 59, I think. Yeah, page 59. All right. So, oh, and let me say one more thing. So the thing that gets tricky about this is, okay, we talked about this one where the mass was at the center, and we talked about changing the position of the mass, but you could also change the position of the rotation axis. So instead of rotating it about the center, I could instead rotate it about the end like this, about this screw. And that changes the moment of inertia. Even crazier is, instead of rotating it this way, I could instead rotate it like this. That's a different orientation, right? So that's so here's one way of rotating it. Here's another way of rotating it. There's one, and then what's the other one? This way. So there's 3 different ways we could rotate about the same pivot point. You could rotate about the X, Y, or Z axis. All right. So now let's go in there and look at this. It's crucial when we're trying to learn about moment of inertia that we look at several different things. Obviously, the amount of mass matters. Where that mass is located. Are the pieces of brass close to the axis or far from the axis? Is the figure skater have her arms out or in? Axis location. Where is it located? For example, here versus here. Is it located at the center of the rod or at the end of the rod? And then what about this one? Axis orientation. Is it perpendicular to the plane of a disc, or is it in the plane of a disc? Notice that causes a difference in the numerical factors, all of these different things. Again, here's one perpendicular to the plane of a plate versus along this axis, which would be different than if it was along this axis. So the way you choose your axis and your axis location and orientation will affect what numbers and letters you need to plug in so that you pass this class. That's what you really care about, probably. But and now if you're a mechanical engineer, obviously this is a huge deal for you. All right. Now, where this gets tricky is every shape has an infinite number of different possible moments of inertia. This will obviously be confusing. So let's start easy. So let's see if I can get this whole problem on the page. Let me make this just a little bit smaller. All right, so let's look at 10.8. And we'll end today with a good summary. So just trust me that I'm going to summarize everything I'm going to tell you at the end, all right? So let's say we have 2 pipes, and they each have mass, and they've got some point masses stuck on them. So what do I mean by this? This is one example of that. You got a pipe here. Now, I don't know if you could see this. I'm going to try to get this on. Let me get this screw out of here. Sorry. Okay, now, I don't know if you could see that, but that's a hollow pipe. Do you see that? So this is supposed to be modeling that. I don't know where that's, yeah. So this is truly a hollow pipe, and there we go. Now you can see it. Okay, so we've got a hollow pipe, and I'm just sticking the screw here so it's easier for me to hold on to this thing. That's all this is doing. This pipe or this screw has negligible mass. And so what I'm saying here is this black rod is negligible compared to these big chunks of brass. Now, big is a relative term. These are not that big, but compared to this rod, they're big. That is what we were talking about. And we could talk about rotating it this way with the point masses far from the center versus right here. I could bring them close to the center like this. And so this is problem 10.8. Let's bring it back. Okay, so that's what I'm trying to show you here. This is the hollow black pipe that I was showing you. Here's one chunk of brass. Here's another chunk of brass. Okay, in one case, they're all the way at the ends. In the other case, they're right on the axis. Now, in this case, let's start with rod 1 and let's try not to overthink this. I'm saying let's get the total moment of inertia for the entire shape by taking this rod and getting the right formula for that. And then I've got 2 point masses. We better get the right formula for that. So let's go up into here and just tell me, which formula should I use for the rod? Obviously, it's one of these two here. Let me circle it. Which one looks like it applies? The 1/12 or the 1/3?
The top one, the 1/12?
The 1/12. So this is going to be 1/12. What is the mass of the rod in this case? Okay, the mass of the pipe or the rod is m, and the length. So that's straight up. It's just 1/12 ml squared. Okay, so now I want to add to that the point mass. So let's go up here. Whoops. Here's a point mass formula. Notice, what does x mean? It's the distance from the axis. So for these 2 point masses down here, they're both the same distance. What is the distance from the axis?
Half L.
L over 2, half L. Okay, so for this particular one, we know we're going to get the mass of the point mass, which is actually 5m. The point mass is 5m. And then we're going to do L over 2 quantity squared. And then there's actually 2 of them. So you'd have to take this whole thing and double it, right? Because they're both the same distance away. 1, 2. Now that you could plug in a bunch of numbers and you get some weird decimal. You could plug it into a calculator if you want. Okay, so that's rod 1. What's going to be different for rod? Oh, let's see. It's 1/12 because of the axis. Yes, through the center. Through the center. That's why we chose the 1/12.
Gotcha. Thanks.
Yep. And actually, I should make that orange. Okay. So what about rod 2? What is going to be different for rod 2?
The point mass.
Yeah, what's going to be different about it?
It's going to be 0.
Yeah, so x is equal to 0 for those ones. Now, that's okay. So if we're treating them as point masses, the distance from the origin is 0. Cool. Now, let's do that. Let's take a look at these solutions really quick and see if there's anything else on there. So there's the first one, and there's the second one. So we see, notice these numbers here. Let me make this a little bit bigger. I just want to point out, in the first case, this term is almost all of the contributions, right? Compare it. The rod by itself is 1/12 ml squared. So here, 30/31 of the entire thing. So 30/12 ml squared is this term right here, right? So notice there's a 4 here when you square it. So you get 2 squared, which gives you a 4. 4, we can cancel out one of those, make that a 2, and get rid of one of these. And then you multiply each by 6, right? Top and bottom. That's how you get the 30. But yeah, a decimal would probably be a smarter way to go now. But yeah, what does this mean? This moment of inertia is about 30. Well, it's 31 times bigger, right? So if you include this 1/12 here, it's 31 times bigger rotational mass. So what is that saying? In this case, it's much easier to rotate this thing when the masses are close to the center versus far from the center. Now, I should be careful when I say that. We are assuming you're grabbing this thing and starting it from rest. A large moment of inertia is very similar to a large mass. If you have a large mass, it's very difficult to change your motion. So a train, it's very difficult to get a train up to speed, but it's also very difficult to stop a train. Similarly, it's very difficult to start this thing rotating, and then once you do, it's hard to stop it as well. So a better way of describing moment of inertia would be, say, something's ability to resist changes in rotational state, but that's too many words. So if you say easy to rotate or hard to rotate, and you hope I know what you mean. But basically, a large moment of inertia, you resist changes in rotation. Okay. All right. So now this begs the question. I just want to point this out. Let's look back at this one. When this thing is sitting right here, whoa, geez, right here and right here, we could probably do a little bit better. And we could assume that both of these are sitting right here. And actually look at the table again. I'm going to show you this one. Actually, look at those. If these point masses are sitting right there, they actually look more like something other than point masses. Remember, these are cylinders. Which other object in the table up above best represents them? If I number them, 1, 2, 3, 4, which number is going to best represent those gray cylinders? We've got 10 shapes there, and let's see what the chat says. Yes, it's 6. Take a look at it very carefully. Oops. Look at this one. Look at this one. Don't they look the same? It's a axis through the face of the cylinder. If I could show you right here, right? That's like saying an axis right here through this thing. That's about what this looks like. Again, we're making an approximation because they're not exactly on top of there, but you could argue, it's basically a disk right on. So if I look at that, let me go to the solutions. So let's say you're upset at me and you say, look, those point masses do contribute to the moment of inertia. Each gray cylinder is actually a disk with an axis through its center oriented in the plane of the disk. So I could use that one. If you did that and did all the math on it, here I did it, it's less than a 5% correction. So I chose to ignore that in this case by just treating them as point masses distance 0 from the center. Is that correct? No. Is it approximately correct? You bet. So this is one of the issues we're faced with. We're always making approximations. In particular, when is it okay to treat something as a point mass and when is it not? I promise to come back to that later today. For now, let's just not talk about it. In problem 10.32, so about 20 problems from now, we'll talk about that. I promise you. All right, let's go to the next problem. And before we go on, are there any questions about 10.8? Ask me anything you want.
I don't really understand, like, so this axis down on 10.8 is going through the middle and like horizontally, but you say it's going like through rod 1's point masses there. It's through them?
It's not going through rod 1's point masses. Okay, it's literally this. The idea is this is a disk. Okay, forget the hole in the middle. Just pretend this piece of brass is a solid disk, okay? All right. And then here's the other one out at the end. And now I'm sitting here holding this thing about its center and I'm pointing it at you. And I'm going to try and spin it this way or that way, one of these ways. Cool? And so now notice this is a cylinder sitting way out here. And my claim is if this cylinder is far away from the center, who cares what shape it is? It's going to basically be a point mass. I'll prove that to you in 10.32. So that's rod 1. Got it?
Got it. Okay.
And rod 2 is just bring them really close. Whoa. Bring them really close to the center. And I can't do this and still hold on to this. I'd have to take the screw out. But imagine if both of these were basically right on top of this screw. that would be case 2. And again, I'm rotating it about that screw like this. So this is rod 2, right? I think in the book, I drew them vertically so I could fit the pictures. So here it's just doing this versus doing this. And you can see it takes a little bit more effort for me to change the direction when its masses are far away. Is that good, Jake?
Yeah, thank you.
All right. And so now let's see what happens if we do it this way. So now let me see if I can get all this on the same screen. We're using the same object. Now, look at 10.9 here. Which rod do you think will be easier to twist? Rod 1 or rod 2? Or is
Rod
it
1.
And why do you say rod 1?
Because so at the top, the point mass is going to be 0.
So this one doesn't contribute at all. Okay.
Right.
Whereas here, they
Yeah.
both contribute.
Yep.
However, now that I said the word however, what do you think? Uh-oh. What matters more? X squared. So here you have twice the distance squared versus here you have twice the mass, not squared. I suspect rod 1 will actually have a larger moment of inertia. It's going to be close, though. It's going to be close. So now what's going to differ in our calculations? We're still going to use I total is add up the pieces. What's the equation I would use for the rod this time?
1/3.
1/3. Yeah, 1/3. So we could see that they look very similar, but if the axis is at the end, you got to grab the equation at the end. So the fraction's going to change a little bit. So let's go look at this one and see. And so, all right. So if we do this about the two ends, this is probably I should have put a decimal here. So 16/3 versus 17/6. Which of those numbers is bigger?
1.
Yeah, by about a factor of 2. Do you see that? And it comes from, you get this L over 2 squared. So you get an L squared over 4, which cuts this term down a lot, which more than compensates. Yeah. So basically here we see there, I don't know. Jake, is that it? You got it?
Yeah, I think I see it. Cool.
Yep. So regarding your question, Mark, this will relate. So let's go big picture for just a brief second. So if you remember, why are we talking about this? Okay, so you might know sum of forces equals ma. Well, if we want to do the rotational equivalent, the sum of torques is equal to I alpha. And so if we want to understand angular acceleration, which relates to rotation rates and such, like the kinematics, we need to understand this one piece. So all of today is just making sure you understand how to get this one piece. And today is all you need to really get that if we spend our time on it. Here's another one. Translational kinetic energy is 1/2 mv squared. Rotational kinetic energy is 1/2 I omega squared. Now, if you're wondering, how do these two relate? Let me just do this for a point mass. Check this out. If I have an object that's going around in a circle here, and this is some radius, and this is some mass, and it's moving this way, let's say it's rotating at rate omega. How does V relate to omega? It's not your omega, it's It's not your omega, it's
Our omega.
our omega. So bad. But if that helps you remember, cool. Take a look. What happens when you plug that into there? What do you get? 1/2 mass times r squared omega squared. Why is moment of inertia defined in this weird way? It has to do with mass and distance from the axis. Now, this is for a point particle. It gets tricky if you have an entire plate. And so every single point in the plate has a different distance from the axis. Whoops, sorry. If you were trying to rotate a plate or a rod, every single point in the plate or rod has a different distance from the axis, but it's going to relate to this original definition. So why are we doing this? Because if we want to understand rotational motion, we need to understand the rotational equivalent of mass, and that's what this is. Any questions about that? All right. That's why we're doing this. Okay. Yep. So it will relate to omega and alpha and all that junk. That said, let's dig in and just make sure we get this right first. So let's forget about that for the time being. All right. Let's look at 10.10. Which one should be easier to twist, rod 1 or rod 2 in part 10? What's your gut tell you?
2.
Okay. So what do you think I'm going to say next? It's not 2 is easier to twist.
Rod 1 because it's the what's it called? The point masses are 0.
No, not rod 1 either.
Equally.
It's a tie. Look at this. If I'm so this is what's different. I'm rotating it like this now. I'm trying to show you this thing, but okay, so like this. I'm rotating it like this. So if I could show you right on axis and hold it right on there. Where is that camera? I forget. Oh, there it is. Whatever. Okay. So this is really hard to do, but I'm rotating it this way, right? Well, does it really matter if I put the masses here or there or anywhere? They're the same distance from the axis. They're on axis in both cases, right? They're on the axis here because the axis is the black rod now. So it doesn't matter where you put the masses. They're all in the same distance from the axis. So remember, figure skater, arms out, mass far from the axis. If you have the mass far from the axis, when I'm rotating it like this, hard to rotate. Here, everything is on axis. So they're both equally easy to rotate. Okay, so now in this case, look at this. This is just a rod with 2 point masses, and look how much time you could spend on this. You could spend a lifetime on this problem probably, but we got to keep going. Here's the deal. In this part, if we treat everything as a point mass, the moment of inertia is essentially 0 because everything is on axis. So at this point, because you would get 0 as an answer, we can't treat the gray cylinders as point masses anymore. We have to treat the pipe as a ring and each gray cylinder as a disc. So the pipe is basically this shape and the disc is this shape, I think. Oh, wait, no, it's not that shape, is it? Why is this not right?
The axis is wrong.
Exactly. We need an axis coming out. So it's actually, let me make this just a little smaller. Sorry, I can't quite see it up there. Sorry. The idea here is this is the black rod now because it's a black pipe that's that long, and it basically is the same thing as that thin ring. And then you have 2 point masses that look like this now. They're now gray discs on axis. Oh my gosh. So when you do this one, let's go in here and look at it. Now, I want to show you something here. Whoa. Annotate. Let's clear those annotations. And let's, come on now. Let's make this 150 so I can see all at once. So in this case, I think I actually tabulated these different moments of inertia, and you can see all of them here. Notice the units are kilogram times meters squared, mass times meters squared. And here's all those numbers summarized. And in this case, notice how much smaller the moment of inertia is for 10.10. Right? This one's pretty small. It has 2 zeros, but this one's still 10 times smaller than that, approximately 3 zeros. So this is crazy small. Now, believe it or not, I don't know if there's any chemists out there. This is important to chemists. I don't know if you know anything about rotational spectroscopy, but think about this. You probably know what spectroscopy is, or spectrums, spectra, excuse me. So different colors of light are emitted. Well, imagine this is a very simplified model of O2. Forget the mass of the black rod. This is one oxygen molecule. That's another one. You could rotate this way, and that's associated with some amount of energy, and that's quantized, and that produces one color of light. You could also rotate it this way. It turns out in this case, that's the same. So, right, rotating it this way and rotating it this way, those effectively have the same moment of inertia. But now rotating two oxygen molecules like this would be exceedingly easy because oxygen molecules are basically point particles. Think about it. Even if you think of this as being the size of the oxygen molecule, this is like the electron orbit. The size of the actual nucleus is much, much smaller, 10 to the 5th times smaller. So it's a millionth of that, basically, way inside there. And so it takes no energy to rotate an O2 molecule this way. So you don't notice spectra from this moment of inertia, whereas you do from this one or this one. And you could do CO, you could do others. This is a whole branch of spectroscopy called rotational spectroscopy. And if you look it up later, you could see rotational spectroscopy, moment of inertia, chemistry. It's all over the place out there. So at some point, you're probably going to have to learn that. So if you're a chemistry major, that was your problem. All right, cool. Oh, there you go. Gonzalo says they use it in OChem. All right, there you go. All right, so that's kind of what we're talking about here. Now, obviously, it gets more complicated. I've just talked about diatomic molecules, but you know, there's a lot of popular diatomic molecules, so that's a good thing to discuss. All right, so now let's get back into here. I just mentioned that we talk about R squared times the amount of mass. So imagine you had a point particle here. Let me go to the whiteboard. That's this one. So let me do a simple case here. So we have a couple of challenges here because not everybody has Calc 3. So let's just start with an object like a square plate, okay? So just so you can see the thickness, I'll draw the thickness into the board just for once. So this is a thin square plate. Whoops, sorry about that. And let's say I bolt this thing around the corner here. What would this look like in real life? This. Pulled my cable out. Sorry about that. Can you hear me? Okay. So that's this right here. The red dot is the pivot point. My fingers are the pivot point, right? So what if I want to talk about swiveling this thing around? All right. Now, I know that this particular point could be treated as a point mass. So could this particular point, and this particular point, and this particular point, and this particular point. And all of these are actually the same distance away. So you could actually say this distance right here is the radius from the axis of rotation, just like a point mass. And then you could say this little slice has some mass dm. And then what do I want to do? I want to add that point mass or that chunk up with this chunk, up with that chunk, up with that chunk. And so what we could do is we could add up or integrate all of the different r squared dm's and get the total moment of inertia of this entire thing by adding it up out of point masses. So far, so good. Now, in practice, this becomes very nasty very quickly. Let me show you something here. If you recall from problem 1.50, every problem's precious. This thing right here is the volume of a thin cylindrical shell. I'm not trying to waste your time with all these crazy problems. Every single one has got a use at some point. I want to do as little work as possible, and I'm not trying to waste your time because it wastes my time too. What problem 1.50 was foreshadowing this and some other things in other problems, other classes. So great. This is in theory how you would calculate this. If you know 3D calculus, that makes sense to you. In practice, we can simplify them by using some subtle techniques. But before we do that, I just want to point out, you don't get a choice of how you slice things anymore. All points in your slice are required to be equidistant from the axis. Otherwise, they don't have the same value of r, and then the integral doesn't make sense. So your slice must be created such that all points in the slice are equidistant from the axis. And you might think it always has to be a cylinder, but in practice, we can skip all that by looking at these three cases, and this will handle most of what we need to know. If you have a rod, you could imagine cutting this thing into a cylinder, right? I'm trying to draw the cylinder right now, a cross section of it. And when you do that, really all that matters is this one little chunk right here. So instead of worrying about the entire cylinder, we just worry about a chunk that has mass lambda dx, just like we did in center of mass. If we do a triangular plate or a square plate, or basically some kind of thin plate, notice I could imagine, again, this cylinder here. Sorry, it's not a perfect cylinder. But instead of cutting up into cylinders, I'm just going to cut it into strips. So I'm going to look at one side of that cylindrical slice. And because it's not 3D, it ends up being just a rectangular strip. So the height times dx would get me the area that I need to get dm, just like in center of mass land. Finally, what if I have a cylindrical plate in like this case? Now, to be clear, the axis is through the center running out of the page. So this is like looking at that piece of brass on end. Right? Let me just get it here. Right? The idea here is if I look at this, you could build up this piece of brass out of thin layers of brass, slicing it up into rings, right? So you could build up this whole piece of brass by building it up out of rings. If you want to think about it, imagine this is a roll of paper towels. You build up the whole roll of paper towels out of individual paper towels that are thin. That's the idea. Okay. So in this case, 2 pi r dr. Well, how am I getting that? Problem 1.50. 2 pi r is this distance right here, all the way around. If I unwrap that and lay it flat, this distance would be 2 pi r. Now the thickness here, that's dr, a small amount of change in the radial direction. So the thickness right here, when you unwrap it, is also dr. So that's where this comes from. All right. We're going to do the calculus in a minute here. But here are 4 main parameters that vary during practical computations: the location, the size of the object, the density, is it uniform or is it non-uniform? And the axis orientation. Always think about that. The first two parameters affect the limits. The third affects the integrand, what you put inside for lambda or sigma. Excuse me. Would you put in a uniform or non-uniform? And the fourth parameter, let's worry about that later. That's the hardest. Okay. Look at 10.11, people. Page 61. Okay, you got the following things are stated. It's a 2D problem. We're doing a uniform density. Says it twice. We have length A and height B. Total mass is M. And we want to rotate it about the y-axis shown. So here's the y-axis. Got it. Which of these two slices will give us the same value of r? Remember, we're trying to do this integral, r squared dm. R means distance from the axis. Which slice gives us the same value of r for every part of the slice? Is it the horizontal slice or the vertical slice?
Vertical.
The vertical slice. Caught me off guard. You answered so quickly. I was drinking while you... Sorry about that. So we do not want to use this horizontal slice because it does not work. It does not have the same value of r for everywhere in there. Okay, so now let's go ahead and crank this out. I'm going to write this up. You guys can start writing it up if you want. I'm going to get it on my board and then I'll share screen. 10.11. Got a disk here. Got an axis here. Let's see. We're told that this length is B. And this length is A. And you just told me I need to use the vertical slice. Okay. And I think we were told the total mass is M. That's also known, I think, right? Okay. Our goal is to do this integral. The integral of r squared dm. Now, just to keep this straight, I told you there's an infinite number of possible answers for moments of inertia. So this one happens to have a special name. In a lot of engineering textbooks, this is called IYY. So it's about the y-axis. I will go into why I use two-letter y's later. I don't want to talk about that now, but this is the standard engineering way of writing this. IYY means moment of inertia about the y-axis. Got it. So in this case, it's the integral of what's a good name for this distance right here?
X minus B or
But just x.
X.
Because do you agree when I start right here, x is 0. When I go here, it's just the x coordinate of that strip. Is that cool, Alonzo?
Yeah.
What's a good name for this thickness right here?
dx.
Dx, a small amount of distance. And the idea here is we're going to slice this thing up so skinny that dx is hundreds of times smaller than x, so we don't have to worry about the distance of the... Here's the deal. If you don't slice this thing up really skinny, the left side of the slice is slightly closer to the axis than the right side. But as long as dx is hundreds of times smaller than x, that's not really a significant issue. It's a negligible correction. And if it is a problem, cut it up 10 billion times smaller than that. That's the joy of calculus, right? You could slice it infinitely thin, and then we'll get an exact result. So now, what is, okay, we want to do r squared dm, right? Let's focus, eye on the prize. R squared dm. What should I plug in for r in this picture?
X.
X. So this is going to become x squared. What is dm in this problem? Is it a 1D, 2D, or 3D problem? 2. So should I use lambda, rho, or sigma?
Rho?
Nope. Rho is 3D.
Oh, sigma.
Sigma. So dm should be sigma times the small amount of area. This is the mass of my slice. That's kilograms per meter squared times the area in meters squared of my slice. So remember, this has to have units of kilograms. So my slice is 2D. If I have a 2D object, I need a 2D slice. That means I need a 2D density. Okay, what is this particular area? What's the area of that rectangle?
Delta X times A.
Correct. This should be area, oh, sorry, not area, A, that, the height times the width, which is dx. So far, so good? What are the limits? Here's the origin. I'm doing an x integral. What is the left? It's not 0 to a. What is the x? X goes left, right? So what is the leftmost value of x?
Oh, negative. Or
Negative b over 2.
Oh,
Does that make sense?
yeah.
That's tricky. All right. So we're going negative b over 2 to positive b over 2. Woo! What do you think? Any questions on that integral? I'm going to share screen with the solution, see if there's anything we missed. Basically, from there, it's just math. Boring. Okay. There is something weird that pops out in this one, so let's see what it is. Whoops. Okay. So, oh, what was sigma? I forgot to tell you. Sigma is total mass over total area. Sorry about that. I wrote a sigma here, but let's look. I know it's the sigma equals mass total over area total if what word is used in the problem?
Uniform density.
Uniform density. And unless I specifically specify it's non-uniform, we assume this is true. If it was non-uniform, I'd give you a function instead of that. All right, sorry, I forgot that. Let's see what else I wanted to say. Maybe today's Zoom. Okay, there's dm. Hopefully that makes sense. Ooh, one of the a's drops out. That's cool. I think that was the thing. And so now we're going to integrate this. Now, at first, you might not see it, but remember, we're integrating x squared. These are constants. They pop out. You get x cubed over 3, right? And so when you get this x cubed over 3, but then you have a b over 2 and negative b over 2, that's going to end up doubling it. So if you know this from calculus class, we have an even function. This is an even function, right? So here's x squared, right? I know that the area under this side of the curve is equal to the area under that side of the curve if we have symmetric limits. So I could actually chop this out and go from 0 to b over 2 if I remember to double it. Blah, 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 blah. You do a bunch of math, you get 1/12. Well, normally we're not going to do this integral because we're just going to look at the table, which you just derived one of the numbers in the table right here. That's exactly the problem we just did. So if you're wondering, how do they get these strange numbers? That's how they do it. All right. I'm going to pause and see if there's any questions. We just did this problem, 10.11. What do you think? hopefully you would never use this integral process. I'm trying to pick one that we know the answer to so you could see how we got it. That's why. Normally, you would not do an integral for this. You just plug it in. How about this one down here? Still 2D, still uniform density, same uniform rectangular plate, different axis of rotation now. So we're going here. Do you think the moment of inertia will be bigger or smaller? What's your gut tell you? Or will it be
Bigger.
the same? What's that?
Bigger.
Bigger. Why do you think it's going to be bigger?
Has more material swinging around than the previous problem.
They had the same amount of material spinning around.
The axis is more towards one side.
Yes. So this one has mass far from the axis, and this one has mass close to the axis, right? There's some close to the axis here, but not as much. So said another way, this lower problem is more like figure skater arms out than this one is. That's a weird way to say it, but maybe that makes sense. There's more mass far from the axis. All right. Good intuition. What's going to change? This is the integral we used in the last problem. What's going to change?
What do the limits change?
Yes. What's the lower limit going to be?
0.
And the upper limit?
B.
And that, as a result, because you don't have b over 2 cubed, we get a much larger term here. And so, good job. That's the main difference. What's going to be different if we do this one? The triangle.
Would it cut it in half or no?
I was going to ask that in a minute. Let's come back to that question in just a minute. Well, actually, let's do it now. You brought it up. So Alonzo says he thinks the moment of inertia would cut in half compared to the rectangle. Anybody else want to validate his opinion or not? Or what do you think? By the way, I'm going to ask you a lot of questions, and a lot of them are tricky. The more you speak up and get told, nope, that's not it, the fewer mistakes you make on test day. So try and fail a lot today, okay? It's okay to fail. What do you think? Does the moment of inertia get cut in half or not?
My gut says yes, but my brain probably says
No.
Jorstad.
It's Jorstad. I'm asking you this because it looks like it should be cut in half, but it's not. So somebody said no. Was that Gonzalo?
Yeah.
What do you think? Is it going to be more than half or less? Like, let's say this one is 6 kilogram meters squared, just so it's easier to talk. It's not 3. Is it slightly more than 3 or slightly less than 3?
I think it's slightly less because
Why?
by cutting it in half, you're not cutting the moment of inertia in half. You're actually just shifting the center of mass.
The center of mass is now closer to the axis. Do you agree?
Yes.
So we see more mass close to the axis. We got rid of all this mass far from the axis. This one may end up only being about 2 kilogram meters squared. Got it? So we expect it will be less than half because more of the mass percentage-wise is close to the axis. All right. So we see that moment of inertia is tricky. So how would you calculate it? It's going to look similar to this integral, but not quite. How would it look different? What is this, 10.13, I think?
Yes.
The A would be decreasing.
Okay, so if this is, you're ahead of me there, good. Most of it looks the same. The setup looks the same, except for this is x, this distance is dx, Alonzo said it. He said the mass is not the same for each stripe. Well, tell me. You don't have to tell me the answer in one step. Just tell me what you might try to do. The mass of this slice, is it 1D, 2D, or 3D?
2D.
2D. So should I use lambda, sigma, or rho?
Sigma.
Sigma times what? dx, d area, or dv?
D area.
D area. What's the area of that slice? Give it a name, or tell me what's going on in your brain. How would you get the area? It's a rectangle. How do you get the area of any rectangle?
1/2 base times height.
That's a triangle. Now remember, this is approximately a rectangle. So it should be
Length.
Yeah.
length
Height.
times height, or width times height. What's the height? Give it a name.
L.
Bad idea.
B.
L is oftentimes a constant and it's used for other things. So it's bad for reasons we don't know yet. Yeah, it turns out angular momentum we're going to reserve for L. So what's
H.
usually the name? H, you could do that. I was going to say Y because it represents the Y coordinate. All right. So yeah, pick a name, any name. And then I'll say, no, I don't like what you choose, and pick what I want. There we go. Sounds good. I was hoping you would have picked Y because that's representing the function. Normally, don't we call the height of a function Y? That's where I was going here. But you guys all picked good. L would be fine. H would be fine. It's just from practical standpoint, Y is kind of convenient here. What's Y? Oh, there's a chat there. Mm-hmm. What do I do?
Should be like negative.
Slope x plus intercept. That's the equation of a line. You probably remembered as y equals mx plus b, but I don't want to use m because we're talking about m in another way already. What's the slope?
Would it be minus a over b?
I think so. Where is it? Whoops, I lost my problem here. Hold on. All I see is brass laying around. It's got a screwdriver, metronome. Whoa, there it is. Wait, no, back a page. Sorry. Screwed up there. Yeah, A. So this is negative A over B, I think. You go down A in distance B. Okay. And so what's the intercept?
B. Or A.
A. And then you check it. If you plug in x equals 0, the height of the slice is A. If you plug in x equals B, the height of the slice is 0. Looks good for a linear function. We're off to the races. Got it. Okay. Now, and when you do the math, let's go see what it turns out to be. Ugh, a bunch of math. All right. So, oh my gosh, I can't even, let me, so it looks like, what did I get here? I need to check this. Look at that. Oh, okay. So now look at this one. This is where it gets sneaky. You might be saying, wait, 1/6 MB squared. Isn't that exactly half of that rectangle? or sorry, half of this rectangle, but it's not. You have to remember that the mass in this problem, the mass of the previous problem is twice as big. So it's actually 1/4 of the moment of inertia. Do you see that? So this mass is half as big as that mass. And so it's actually 1/12 of the previous problem. So it's less than half. Okay. Oh, I should be careful here. I should say less than 1/2 of that right there. I need to fix that up. 10.13. I'll make a note. All right. Point being, whoops. Oh, geez. Wrong button. Sorry. I meant to click this button. So it's not really obvious when you first look at it, but this triangle here is less than half of this moment of inertia of the full rectangle if you factor in the density and the total mass and everything. All right. Woo! Now, questions about this junk? I'm going to keep plugging along. Interrupt me at any time. We'll take a break pretty soon here, probably right after the next problem. Take a look at this problem right here. If you have a non-uniform density, it's going to be very similar, only now instead of saying it's lambda dx and lambda is mass over length, it's lambda dx and lambda is whatever lambda is. What do I mean by that? If I look at 10.14, you have lambda dx, and instead of sticking in mass over length, you put in that ugly formula for it. Big deal. Okay. Let's go back to here. I'm going to let you do that one on your own because I think it's not that bad considering compared to other things. But again, this is how you handle non-uniform. What about 10.15? I was alluding to this earlier, and let's actually make sure we do this one so we understand it. So you have a disc of metal and you've got a hole cut from it. Both are on axis. There's a couple of different ways to do this one, but let's start like this. What problem did I say this was? 10.15. Okay. Okay, sorry, that's not a perfect circle. Maynard would be proud. Okay. That's an obscure reference. Now, I'm going to take this object that looks like this, right? A hole in the middle. I'm going to take it and I'm going to try and build it up out of slices. I know that if I snip this and unfold that slice like this, this has a length 2 pi r. The thickness of that slice is dr. It's a small amount of distance radially outwards, right? Sorry, that's so sloppy there. That's a small amount of distance radially outwards.
That's from like the center, right?
That's from the, yes, that's from the very center. Sorry, it's sloppy. Thank you for checking me there. Okay. So now in this case, I know that I, about the z-axis, in this case, the z-axis coming out of the board at you, is the integral of r squared dm. Well, in this case, that's equal to r is literally the distance out to the center, or distance out from the center, excuse me. So that's the radius r. So that's just going to be r squared, and dm is the hard part. Well, that's sigma times 2 pi r dr. What are my limits? What's the smallest value of r I can get and the largest value? R1 to R2. So that's the inner radius to the outer radius, R1 to R2. Now, what's sigma? How do you get sigma? Is this uniform or is it non-uniform? Wait, this one for 10.15 is uniform. So what equation should I use to figure out the density here?
M total over A total.
Correct. Total mass over total area. Well, the total mass is M. I'll do that part. Got it. Don't say I didn't get you anything for Christmas. What is the total area? I want the area of that face, right? How do I get the area of that?
The big area of the bigger circle minus the inner.
That's it. It's area outer minus area inner. Nice. So this will be pi radius 2, I believe, is the bigger one, right? Yes. And you could factor out a pi if you wanted. Cool. All those stupid looking problems in chapter 1 are starting to show up again. Have you noticed this? All those weird problems with holes cut out of it. There was a reason I tortured you with those. It's because I want you to have that skill of subtracting off holes, because we use it at various times throughout this class, the next class, etc. It's easier than doing calculus in sometimes. So that's why we're trying to learn it. It's a shortcut. All right. At this point, let's look in here, and there's a subtle thing that shows up, and don't worry, we're getting to the break right after that. 10.15. Okay, so notice I tried to spend a lot of time on this solution, so if you don't like my sloppy writing, read. Here's that density. Here's showing you that slice, and we slice it up and unravel it. So here's the calculation. Notice we're going to get a, sorry, let me get my annotation here. Because your slice has got a 2 pi r in it, we end up with an r cubed. So you get r to the 4th over 4 when you do the integration. Now there's something cool here. Just trust me. Look at this. You guys probably see that okay. Hold on. This line right here. You could probably see that all right. Does that simplify or not? These are to the 4th. These are squared. Can we simplify that?
No.
Yes. You don't see it right away. Look, you could actually split up to the 4th in this weird ass way. Check that. Do you agree that you could actually split it like that? Take a second to kind of foil it out. This one times this one gives you that one. That one times that one gives you that one. And then the cross terms vanish because they have opposite signs. So this can be rewritten like that, which allows you to cancel out the minus with the basement. Isn't that cool? I have a strange definition of cool. To me, that's cool. All right, so notice in the end, you actually get a plus sign inside. Students oftentimes are thinking, wait a minute, shouldn't you get a minus sign out? No, the minus sign drops out because of an unusual math trick. Now, you might be saying, dude, why don't I just say the total moment of inertia is the outer one minus the inner one? In fact, you could do it that way as well. You could say, here's this one and here's that one. The problem is mass 1 and mass 2 are not the same. And so you have to use this ugly form of the density like that. Oh boy. And you'll get back this same answer. So it's actually faster to do this one. Maybe this might be, I don't know, whatever. It's 6 of one, half a dozen the other. But again, we see you have to watch out when you're comparing things. Are you comparing things that have the same mass, or are you comparing things that have the same density? Again, what do I mean by that? We ran into trouble up here. If you try to compare the triangle and the square using the letter M, you usually get confused and screw it up. If you compare them with the same density, then it actually is easier to see the triangle is less than half. All right, whatever. Basically, just watch out for same mass versus same density in these problems. Tell me which item in the table is used if R2 equals R1. If R2 equals R1, which object do we get? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If R1 equals R2 equals R, which object are we essentially building here in this table? If you recall, the answer was 1/2 M R1 squared plus R2 squared, right? So if R1 equals R2 equals R, which shape do we get? Remember, this is the inner. If the inner radius is capital R, what shape is it? The shape is called being tired. It's this shape, right? If the inner, right, look, the 1/2 drops out because you get R squared plus R squared, and that's 2, and that cancels out the 2. This one is what happens when R1 equals 0. There is no hole. All right, that's what I was trying to get at. So we're going to take our break now, and I'll just foreshadow where we're going. The next step is we want to avoid calculus whenever possible. So we're going to learn about the parallel axis theorem next on page 62 when we come back. So let's come back at 5:57 on my clock, or 10 minutes from now. Okay, 10 minutes sharp. Whew. I'll leave the stream running so I don't forget. Moment of inertia. right, so I'm back. We still got a minute here. I'm checking. Oh shoot, Jesse and I just now saw that in the chat. Sorry, I'm so bad at seeing the chat. It's like one tiny little red dot. So I was kept waiting for an answer, and you guys are like, okay, whatever. They're not answering, but you did. I didn't see it. My bad. Sorry about that. Thank you. All right, so now let's talk about this new topic here, parallel axis theorem. And maybe I'll start. Actually, let's start like this. Okay, so here I have a disk. Sorry, it's such a mess here. Well, what are we going to do here? All right. And so there's a rope on the back here. I just got to bunch it up here and just kind of deal with it. Okay. So right now I'm trying to rotate it about its center right through here. Okay. But, and notice this is through its center, and just being clear, this is a thin circular plate. I want to rotate it about its center, perpendicular to the plane. However, you could say, what about rotating it up here about this point? So now I'm rotating about here instead of the center. I do want to point out that this axis and this axis are parallel to each other, right? If I could hold this thing and not fall down. There we go. So the idea here is there's two different axes. I could rotate it about this one, or I could rotate it about this one right here. And so the idea is these two axes, again, are supposed to be parallel. There is a math trick for figuring out the moment of inertia when two axes are parallel and one of them goes through the center of mass. I'm going to repeat that. There's a math trick when these two axes are parallel and one of them goes through the center of mass. Okay. So if I look at this in the book, I've got some pictures drawn so I can actually talk and draw at the same time. So here's the idea. One of the axes runs through the center mass, two axes are parallel. So just so this stands out, I've got this axis right here, the left one, and I've got this other axis over here, the right one. And let's just say for some reason the center of mass is the right one or the red one. The idea here is that the moment of inertia through the center of mass is related to the moment of inertia through any axis parallel to it by this unusual quantity md squared, where d is the distance between the two parallel axes. D. So, got it. Let's try this out on a problem. Again, we're going to try to use this to analyze this situation. Notice this situation right here, you could solve using calculus, and you might be so fast at it, you'd be tempted to use calculus, but we don't want to have to use calculus for harder stuff. You have to trust me on this. We need this trick. So this does not match up to either of the ones in the table. If you remember, I'll just draw the table here really quick. There was this one where we had a 1/12 ml squared for a rod. And then there was this one. Sorry, it takes me a minute. Same rod. This one was 1/3 ml squared. And what I'm saying is I want you to correctly apply the parallel axis theorem, this thing, to this situation. What? Oh, go ahead.
So the rotating axis isn't technically at the end nor in the center, but
right, it's somewhere else.
okay.
If it helps, give me a sec. Where's that other piece of brass? Find it when I vacuum. Oh man, I have no idea where that brass. Oh, here it is. Sorry, I just don't want to lose these things. Here it is. Here's just the rod. 1/12, 1/3. Now what the hell is it? That's my question, right? It's 1/12 at the center. It's 1/3 at the end. What do you do if we grab it somewhere else, not in the table? Got it? So now let's go back to here. Let's correctly apply. Now, you may make a mistake. I don't care. I want you to try, because if you try, you'll remember the answer better. All right? So I want to plug something into this junk right here. I need to plug crap in. What do I plug in for ICM and for D squared? That's what you got to tell me. Just try. It's okay to screw it up.
Would X be for ICM?
Say again. Sorry.
X? Well, that will be ICM.
Okay. ICM is not X. ICM has to have units of kilogram times meters squared. So it's going to be one of those table formulas. Does that help?
Yeah.
And let's see what the chat says. You say, I see 1/2 mr squared. That's for a disk. So that doesn't work, Jake.
Yeah, I just noticed that. It's
Okay.
1/12 ml squared.
1/12 ml squared would work. And then what is the distance D that you have to plug in?
X?
No.
Wait.
It's the distance from what to what? Help me out.
So from the center of mass to the other axis, right?
Yes.
So L over 2 plus X? No.
L over 2 would be the whole distance here.
Is it
It's not plus.
L over 2 minus X?
Yes. Does that make sense?
Yes.
So it's ugly, but it's correct. Correct and ugly is going to work for us every time. I don't know if you've noticed this. There's a lot of pattern is I deliberately give students questions that are not pretty because real life is not pretty. Hell, we got the coronavirus. You know this. Real life is ugly. Real math is not always beautiful like a math class. Real math is what it is, and let's just get the damn thing done right and get it over with, no matter how ugly it looks. Okay, so that whole distance is L over 2. So that means the distance that we care about between, and so that was tricky. Now, wait a minute. I think that's going to work out. Now think, what should the answer be if X equals 0? If X is equal to 0, where is the axis located?
The center? Or no? At the
At
end?
the end. So what value should you get if X equals 0? Should it be 1/3 or 1/12?
1/3?
1/3. Does it work out? You might not see it right away, but if X goes to 0, you get L over 4, or sorry, L squared over 4, 1/4 plus 1/12 equals 1/3. So that works out. What if X equals L over 2? What should you get? Where's the axis located then?
Right on top of the center of mass.
Yep. And so then we should get back just the 1/12. Well, if X equals L over 2, this term drops out. We get back. So this works. It actually gets the exact result for anywhere on the rod. And that's a lot faster way than trying to do calculus problems over and over and over again. This is a good deal for us. Now I'm going to ask you something. Why don't we do it this way? This seems like it would be a lot easier to me. Why can't I do it this way? Or can I? Here's the moment of inertia about the end. And then here is the distance from the end. Why don't I do it that way?
Is it because you're not including the rest of it?
It's because one of them has to go through the center. And in this case, both of them don't go through the center. So it's not a valid way to do it. You don't get to choose here. You have to have one of the axes go through the center. Is that good, Alonzo?
Yeah.
Yeah. So while it would look prettier, it's totally wrong. And then missing everything in the rest of the question because you tried something that looked pretty is not fun. So ugly and correct is better than pretty and wrong. Okay. 10.17. A solid sphere has an unhappy face painted on it for no good reason. What's the moment of inertia if you rotate it there? About that side. And I'm looking for a sphere here. All right, hold on.
Would we use the 2/5 mr squared plus and then the radius?
Yeah, the distance would be the radius. So instead of rotating it like this about its center, right? Instead of rotating, oh gosh, this is hard to do. Instead of rotating it about its center like this, we're grabbing it about its edge and rotating it like this, right? It's a weird thing to do. I like to think of it like this. Imagine this is a punching bag, right? It's rotating about the top point. So there's a practical application of how you might do that. And then if you run out of punching bags, you could just use, say, like a student's face or something, right? That's a joke. That's a joke. Bad joke. All right. You just use a sphere and write the word canvas on it. And then but then you might break it on the first punch. All right. Let's get back into it. All right. So here in this case, you could just pretend that's my face on there. All right. So in this case, it would be 2/5 mr squared, which is the moment of inertia of a sphere about its center of mass. So that's I, center mass of a sphere. And then we'd add to it, the distance you've shifted is actually the radius. Now, I mention this because it comes up all the time. So you'd say mass times radius squared. And notice, I think we're going to get 5/5 plus 2/5 is 7/5. Got it? This is going to show up a lot. So just be ready for that over and over and over again. It's very common for things that are rolling on a ramp to shift the axis by a distance r. All right. Let's go down to here. I'm going to make this a little bigger. So you have a bike wheel hanging on a nail. The thin ring has mass m and radius r in each of the three spokes. So everything's mass m. All right. So we're looking at this one. I'm going to make it even. I'll just do it on the board. Okay, we're getting nastier now, right? This is the object that we're looking at. I forgot which problem this is. Can somebody shout it out?
10.18?
2.18 or 10.18?
Yeah.
Thank you. All right. So you don't have to tell me the answer to this, but how might we approach this thing? If I want to figure out the moment of inertia, if I put the pivot point right here, This is too hard to do it all in one step. So maybe just tell me something you would try. Anything.
Maybe use like the ring and then the parallel axis theorem.
Okay, we could do the parallel axis theorem on the ring by itself. What if, I'm going to propose an alternate idea. What if you first figure out the moment of inertia about the center? Do you agree that's the center of mass for this whole wheel? Even though we haven't done the math for it, I think you could see by symmetry, usually the center of mass of a wheel is at its center, right? And in this case, you'd say, oh, there's some up, there's two parts up and then one part down, but these are angled, so they're good. Left, right, it's really easy to see it's centered left, right. Agreed? So we expect the center of mass to be right in the middle. And so rather than do the ring by itself and shift it and then the three spokes, let's do all of it and then shift all of it by distance r. Does that make sense, Jake?
Yeah. I'm not exactly sure how you'll do it, but yeah.
Okay, let's do this. What's the moment of inertia of the thin ring about its center of mass?
mr squared.
Mr squared. Now, how do we get the moment of inertia of this weirdo thing?
Would it just be 3 thin rods?
3 thin rods. Which thin rod equation do I need to use?
1/3.
Yeah. So I of the spoke, I spoke, is going to be, and this is about the end, is a 1/3 mass. Now, what's the length of each spoke in this case?
R.
R. And since we have 3 of them, if you put this all together, don't we just get 2 mr squared? 3 of these plus 1 of those is 2 of those.
Yes.
And then what's the total mass?
M.
What's that?
M.
4m. 1, 2, 3, 4 pieces that each have mass m.
So they're
Each
the
spoke
same-
is mass m. Yes. The problem said each spoke has mass m and the ring has mass m. This is a terrible design for a bicycle wheel, but so what? And then the distance it shifted is r squared. So the total is actually 6 mr squared. What do you think? Being clever is nice. It's better than doing calculus. I'm telling you, if you tried to figure out how to integrate this, it would be impossible. Now, I'm not lying to you. You got to do this stuff where later on we're going to have, most of the time it's rods and point masses or a cylinder with a disc on it or something. But usually you have to do something where you add 2 pieces together. And for one of them, almost always you have to do the parallel axis theorem. So in this case, it was for the combined bunch. So I'm not trying to make this harder than it needs to be. It's just, this is the level we need to be able to deal with. All right. And that's about it. For the most part, most of these problems are going to be kind of like this one, where you get a couple of pieces and put it together. All right. Now, normally I used to teach this class every fall, and then this would actually be right around Halloween when we cover this. So questions 10.19 and 10.20 have Dracula and Frankenstein involved. So let's kind of pretend it's Halloween right now, all right? Dracula, I do not need calculus for a moment of inertia, solid light axis, man. Hey, don't you know, man, it's so easy, don't you know? That voice is actually taken from a guy I used to wash dishes with. I used to be a dishwasher. His name was Zoltan. Hey, Rob, man, don't you know Rob? Anyways. So in this case, Dracula or Zoltan, however you want to say it, he says, look, earlier in the textbook, you told me the moment of inertia of the triangle about the dotted line is 1/6 ml squared. And so I'm going to try to use this calculation to figure out the moment of inertia about the solid axis, because in this case, the dotted is parallel to the solid, and the distance between them is L over 2, and I got to square that. So Dracula says, oh no, oh man, don't you know I get a negative answer for moment of inertia? That is clearly wrong because it's always positive. You had a lot of garlic. My students are going to tell Dracula what's up. Why is this wrong, people?
Is it the wrong axis of orientation?
It's not the wrong orientation, I don't think, because
It's
both
not in
of
the right
these,
position.
they're, what do you mean it's not in the right position?
The axis is supposed to be 1/3.
It has to be, one of the axes has to be at the center of mass, which is 1/3 from the fat end, right? And so what you could do is first go to this axis, then go over to the next axis and use the parallel axis theorem twice. Yeah, nice, everybody, nice. Good job. So the correct answer equals 1/12 again. How crazy is that? All right, whatever. All right, so let's go on to the next one. Dude, I've got this uniform disk. I know I read the table. Uniform disk is 1/2 mr squared. And then I did the parallel axis theorem and I got 3/2, deuterino. My physics teacher says I'm full of it, but whatever, man. Why is Frankenstein wrong? Anybody see it? I'll bring up the chat in case you're putting it in the chat. Can you see the mistake in Frankenstein's procedure? It's there. There is a mistake.
The ICM equation's wrong, I'm pretty sure.
Yeah.
It would be 2/5 mr squared.
Well, no. 2/5 is for a sphere.
The axis is wrong, right?
Yes, this is for the axis running out of the page, which is not parallel. If you want it like this, which is parallel, the moment of inertia you should use is
1/4.
1/4. So you're on the right track there. So this is why the parallel axis theorem is diabolical. You have to remember, you get so spoiled using this equation over and over again, you forget one of these has to be at the center mass. And you have to make sure it's actually parallel. It's the parallel axis theorem, right? Not the perpendicular axis theorem, which is on the next page. So the perpendicular axis theorem, I'm not going to lie to you, I probably won't get this too involved on your test. But I'm showing this to you because I think you need it for 1 or 2 questions in the homework. Sometimes I make the perpendicular axis theorem an extra credit question. Those of you that are going to be mechanical engineers or whatever, you should probably just learn this now because you're going to have to know it. This result is only valid for objects in the 2D plane. Basically, you do this weird trick here, and it turns out the moment of inertia about the z-axis out of the page, so about the axis out of the page, you could actually sum it up by saying, look, I'm going to add up all these chunks. Well, that gets you an x squared plus a y squared, which is the moment of inertia about the x-axis plus the moment of inertia about the y-axis. Really, really cool. And as a result, you could see, like, let's say we have, let me do it this way. I've got my trusty cylindrical plate, thin cylindrical plate. So the idea is rotating it this way is pretty easy because most of the mass is on axis. Rotating it this way is pretty easy because most of the mass is on axis, but rotating it this way is a little bit harder because the axis is now this way and a lot of the mass is far away. So the idea is Ixx plus Iyy is equal to IZZ. That's what I'm trying to show you here. So, and this works for, there it is. This works for this book, right? IXX plus IYY. Wait, I screwed it up. IXX plus IYY is equal to IZZ. Now, again, we're not going to focus on this too much, but it's used in 1 or 2 homework questions, all right? So it could save you some time. If you want, you could see how you might do all these things, and you could, all right, so this is kind of a fun problem. The idea here is, if we want to figure out the hoop about this axis, we need the perpendicular axis theorem, and then we could shift it over using the parallel axis theorem. So this uses perpendicular, and this uses parallel. You could imagine splitting this into 2 triangles, right? And you could get the moment of inertia about this one and the moment of inertia about that one, and then you could add them together, and then you could do it out of the plane, and oh my gosh, it gets tricky. All right. But here's a summary of this junk, okay? In this case, the first thing you do every time you have, so you're probably tired. Let's wake up, people. Let's get the summary down, all right? So focus right now. Okay, here we go. First, make sure you identify the location and orientation of the axis correctly before you grab something out of the table incorrectly. 2, hopefully you can just split something into parts and add it up. Remember, if it's got a hole in it, you could do a subtraction here, right? So you could either add pieces or subtract them. Now remember, if it's similar to the table, but it's shifted parallel, and one of the axes goes through the center of mass, then you can use this parallel axis theorem. If it is a planar object, a 2D plate, and we're looking at the table and you don't see it and it's out of the plane, basically you could say this equation is valid for objects in the XY plane if you're looking for the Z-axis. Similarly, if you had the XZ axis, you could say XX plus ZZ equals IYY, but whatever. And then finally, you could always use calculus. If you have a non-uniform density, we pretty much have to do this. Some information to give us intuition. When most of the mass is close to the axis, the moment of inertia is small. If you have a small I, it's easy to change your rotation. For any chosen axis orientation, I center of mass is always smaller than any parallel. You might think this is silly, but this is a way you could check the parallel axis theorem to make sure it's working correctly. This number is always smaller than that number, regardless of the value of D. No matter what value of D you add to it, the center of mass should always be the lowest moment of inertia compared to any axis parallel to that. Okay, so I center mass is always smaller than any I parallel. And then for planar objects, the moment of inertia out of plane is always bigger than the moments of inertia in plane. Out of plane is always bigger than these two because you have to add 2 things together and everything is positive in here. All right. Questions on that summary right there? Any questions about any of that? I guess I should have said the page. This is on page 64. I'm sorry about that. All right. I'm pausing for a second. We still have 20 minutes. I'm going to do some rapid fire types of problem setups. This is our goal for today, so we're doing great. This question is, whoops. This question is a really good one. It's a combo question. The idea here is you do this problem first and do a bunch of math. And then, question, go ahead. Oh, my bad. Okay, so you're going to do this question here first, do a bunch of math and figure this thing out. what happens if you rotate it about the x-axis, the y-axis, the z-axis, and we'll see if you know what you're doing. Next, what is going to change and what is not going to change if you relocate the hole? Without doing the math, you could check yourself and see, should the center of mass change? Will it not change? Will only one coordinate change, or will they both change, or will neither change? What about these moments of inertias? Which ones are affected and which ones are not? So even though this one's a bit of a pain, the combination of this one and that one, I really believe will lock in almost all of your understanding. Okay. Not perfectly, but it's a good review question. All right. I spent a lot of time on that one. I hope you can learn from that. All right. So I'll let you do that one at home. Now, how about this one? Let's try this question right here. Whoops. How does choking up on a baseball bat affect its moment of inertia? Let's pretend this is my baseball bat here.
Faster swing?
Yeah, so if I choke up on it, so right now, let's just try and do an ideal situation. Let's say I'm swinging like this, right at the end. Choking up means moving your hands away from the end. So now my hand is closer to the center of mass. If my pivot point is closer to the center of mass, the moment of inertia is closer to its minimum. It's lower. I have a smaller center of mass. It should be easier to change the rotation state. I should be able to get more bat speed on the bat. That's the moment of inertia calculation here. All right, let's try another one. Look at this one. What if you had a gas centrifuge? And so imagine you had some device here. You could imagine some equation like this, where the gas is taking on, well, here's x, and here's e to the negative x squared. If you multiply these two together, you're going to get some function that looks like this, where the gas takes on some strange shape. Okay, whatever. So somehow this gas takes on this unusual shape function. So what? The density is some function. The technique is still the same. You get an integral table. You should be able to do this or plug it into Wolfram Alpha. Believe it or not, similar integrals appear in quantum mechanics and quantum chemistry. So that's why I'm kind of foreshadowing that there. The process that we're doing here of doing these center of mass integrals is moment of inertia integrals is very similar to the process known as normalizing a wave function. So, okay, cool, whatever. This one surprised me. I have two squares. Okay, and so to be clear, we are on page 65. You have two thin square plates. They're made of the same material. Ding, 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 ding. What does this mean when I say they're made of the same material? What am I telling you there?
They have the same density?
Same sigma in this case, same density. Square plate is what tells me it's an area density. Nice. And so all I'm saying is, let's say that this is I1. I'm saying that is, I want I2 to equal 1/2 of I1. And I just did the math really quick, and it surprised me. It's not just half the size, as we've seen all day long. You could go ahead and do that one later. Here's another non-uniform density. Okay, now I'm going to scroll even more here. 10.28 and 10.29. You'd think there's not much I could do to mess with you, but I discovered after giving some tests and just making very slight variations to that one question we saw earlier, I destroyed people on a couple of tests by just changing one or two words. And so you should see what is different in these problems compared to the earlier one. And it's showing you the kinds of wording I might use. There's nothing different about the problem here. It's just the concepts of the problem are all exactly the same. The issue is, how did I word it and what was given and what was not given? So make sure you look at those, okay? Not trying to I wasn't trying to screw people over that year. I just was naturally very good at it. Here's some different ones comparing different shapes. Here's just kind of rank them if you need practice ranking them. Finally, when is it okay to consider a sphere as a point mass? So let me just show you this solution because I think it's useful to understand it. So before I do that, let's remind ourselves what we're looking at here. Sorry, just getting the screw out of here. Don't want to drop it. There we go. Okay. The idea is this. I've got this point mass here, and let's say I'm rotating it about this end. Okay. My question is, when you put it really close to here, we got to treat it as a cylinder. And the question is simply, how far away do you have to move it before you could treat it like a point mass? How would you figure this out? Let me just show you so you're not wondering. Because when I was a student, that drove me crazy. You're like, sometimes you call it a point mass, sometimes you don't. When is it? Well, there is no easy way other than doing question 10.32. So let's go take a look at it. Oh boy. Hang in there, people. So the idea is if I had a sphere, oh, whoops, this was a sphere. So I have a sphere and then I add in the parallel axis theorem, right? This is the sphere, and I'll just draw it on here so you can see it. That's the sphere. And the idea here is you're basically using the parallel axis theorem. You've shifted this thing over some distance x. So if it was right here at the center, I know this would be the moment of inertia. But as you move it outwards and outwards, the point mass contribution or the parallel axis contribution starts to dominate. So what I'm asking is, when does the point mass part of this equal 99% of the total so that we can ignore this junk? I'm going to say that again. When does the point mass contribution from the parallel axis theorem equal 99% of the total so that I could ignore the 2/5 basically? So you do this math, I do this math, I solve for this. In this particular case, it only takes a distance of x equal to 6 times the radius. To be clear, this doesn't work for every shape. Every different shape is going to have a different number in there. For example, a spherical shell like a basketball or a tennis ball would use 2/3. That's a little bit bigger. What about a cylinder? A cylinder might use 1/2, but they're all about the same. It's probably about 6 or 7 times the radius. So going back to here, the idea is, let's say this distance is about 1 centimeter. So that means anytime I'm more than 6 or 7 centimeters from the end, this looks like a point mass. If you want to see what it looks like on a graph, I think you can really learn something from that. Look at this. Whoops. There's the plot. The idea is this is x, the x-axis. It's how far you are from the axis of rotation. In this case, if you're close to 0, clearly the point mass contribution from the center of mass is way off. However, when you get out here to this size, there's almost no difference at all. And as we get higher and higher up, percentage-wise, you can see there's a fixed shift, right? The distance between this line and that line is always the same height vertically. The only difference is right here, it doesn't matter at all. So right there, this is only 4 times the radius, I think, or maybe it was 5 times the radius or whatever. But even at just 4 or 5 times the radius, we could see that, man, the contribution from the 2/5 is negligible. Almost all of it is coming from this point mass contribution. So here's another example. I know you don't, this may seem a little bit weird, but imagine I'm a human being standing on a merry-go-round. Imagine I'm a human being. I know that seems strange, very difficult, but you could try. Okay, you got to be creative. Whatever. As if I'm standing on a merry-go-round, I'm approximately a point mass compared to a large merry-go-round. Now, I'm not a point mass if I'm just spinning around on the ice and I'm not attached to anything else. So choosing to call something a point mass usually means you're a point mass relative to the situation. And so, like this one. Remember this old friend? Let me get this out of here. And you thought you'd never see golf balls on a meter stick again. Oh, were you wrong? So in this case, do you think it's okay to treat those yellow golf balls as point masses? What's your gut tell you? Yeah. Whereas if they were right here, close to the axis, probably not. And if you're not sure on the final exam, what could you do? Ask a question. All right. So if you're not sure, just ask me on the final and I'll be like, oh, I was assuming they were point masses, dude. All right. So, all right. So if you're not sure if something should be considered as a point mass, usually I'll either say it in the problem or you can ask. If it's something I think you should really know, I'll tell you. But usually on that type of question, I don't expect you to kind of know. That's an assumption. So usually that's something I would tell you. In the end, treating something as a point mass almost always gets it right if you're comparing it to like this rod or something. So almost all the time we'll do that. All right. Let's go back into here. We got 7 minutes. I know you're tired. Let's just keep looking at a few more little things. What do you think you'd do for this 10.33? How would you approach 10.33? Just kind of walk me through it conceptually. You don't have to tell me numbers and letters and crap. Or what might you try? I'll give you a second to look at it.
I would first find the center of mass.
Okay. Turns out that's a bad idea. You could find the center of mass, and that might be useful later, but we don't need it.
Find the area of the missing circle.
Okay, could we do that if we're told the radius of it? What's the area of the hole? What's the a-hole? Not your instructor, people. What's the area of the hole? Pi r squared, right? Okay, what else?
Can you do the parallel axis theorem?
On what?
So first you do the moment of inertia of the big circle, and then you add that to the small circle, but you use the, well, you could probably put it like in parentheses.
So yeah, actually, I would actually do minus I2 here, right? I would say, look, I'm going to get this one about its center. I'll get this one about its center, and then I'm going to shift it using the parallel axis. That's the big picture of how you would approach this. So let's take a look at the math of that one and see 10.33. And notice we don't need the center of mass if we split them up. Gonzalo, did that make sense?
Yeah.
Isn't that sneaky? So the idea is it's 1 minus 2. And then here is the moment of inertia of 2. This is the hole about the center, and then you shift it over by distance x. Then you could say, well, they each have the same density. So you could rewrite the masses in terms of density and get this weird formula here. All right. Let's get back to here. Where was that? Okay, that's a fun one. Let's see. Oh my gosh. Okay, page 67. Some of you are math purists out there, and I know it. And you might want to know all the tricks. So to be honest, these tricks on page 67 and to the end of the semester are not not to the end of the semester, to the end of this chapter, excuse me, no, to the end of this section of the chapter, whatever. you don't need to know this, but if you're curious, here's some different ways I worked it out. And you can see here's some different ways to do calculus. So there's one way to get the moment of inertia of a sphere. Here's another way to get the moment of inertia of a sphere where I used parallel axis theorem, and it works out. You could use some of these tricks to do these nastier problems if you really wanted to. And there we go. We made it through not center mass, moment of inertia. Now, let me remind you why we're doing this. Okay, so we need the moment of inertia to do some calculations. So let's take a look, and I'll just point this out. We're going to learn torque next. That's next time. And then the idea is, there's a pivot point here. See that? I could get the moment of inertia about that pivot point, and then I could use the sum of torques equals I times alpha. If we know lots of different ways to get the moment of inertia, you pick one, get I, we do the forces and what we're going to learn next time, and you can figure out the angular acceleration. What do practical problems look like? A lot of times they're pretty easy, where it's just a rod pivoted about its end. Well, that's a pretty easy one. That's just 1/3 ml squared for that one. So I don't need to do a lot of work. What about this one? Oh, crap. How would you handle figuring out the angular acceleration of this thing? Well, you'd need to get torque. What else would you have to do for this problem?
The moment of inertia.
Yeah, we'd have to get the moment of inertia. And what would you have to use to get the moment of inertia?
The parallel
axis.
Parallel axis. So we see that, oh, crap. Sometimes you got to use the parallel axis theorem. All right. Let's keep going a little bit. If we scroll down, let me show you some more. Okay, here's a rod about its end. There's a disc. So a lot of these are going to be very easy to get the moment of inertia. What if you're on the toilet tonight and you're ripping a piece of paper off the roll? And you could imagine, what if the roll has a lot of rotational mass versus almost none, right? How come sometimes you could rip the piece of toilet paper off without holding the roll versus sometimes you need it? That's the answers I know you took this class to get. If you need to know about toilet paper ripping, that's why you're enrolled in this course. Whatever. There's a rod. Where else? Here's a rod with a point mass attached. And look at this fun equation we get to do next time. Right? We're going to worry about the height of the center of mass location. So I need to know where the center of mass is. Then I need to know the moment of inertia so that I can get the rotational kinetic energy. Okay, that's why we need to know the moment of inertia in all these weird shapes. Let's keep going further. Here's a rod by itself, different length rod. There's a rod with a point mass. Here is a circular plate with a circular hole cut out of it because it relates to a cam, right? We like to look about those. What about pulleys? You might be saying, wait a minute, I thought we didn't have to worry about the pulley. Well, let's look on the next one. We'll learn that this is the original Abwood's machine from chapter 5. What if the pulley has non-zero mass? Then its moment of inertia shows up in the equation. I know it's almost time to go. Hang in here. So we could add that moment of inertia thing into there. Oh my gosh, this is going to be fun, isn't it? So we're constantly having to worry about the moment of inertia. Here's one where I have you figure out the number using a torque problem. They do this with satellites. They literally, give me a sec here. You could take a satellite that you're going to send into space and put it on a giant turntable and spin it and calculate how much torque it takes to spin it. And then you know the moment of inertia of the satellite without having to do a bunch of calculus. Not bad, right? As long as you do a good job on the experiment. So yeah, there's imagine how complicated an entire spaceship would be. You'd have I1 plus, that's too hard. So what do you do in a practical world? You just put it on a table and spin it and see how much torque it takes to spin it. If you've been wondering, here's that pulley that we've been looking at all semester with the different radii. What if something is rolling? This is the hardest. You have translational motion as you move from here to here. You actually move in a straight line path. But you also have rotational motion. So we have both translation and rotation. So we have both M and I. We will talk about that soon. I know we're almost there. Hold on. Rolling. We could talk, if you need yo-yos, you need your moment of inertia. All right. We could come back to this one and analyze it with it rolling. Okay. Let's keep going here. Oh my gosh. Bowling balls. If you're going bowling, we need to know that moment of inertia. Oh man, these get hard. These get really hard. All right. Angular momentum is the last piece of this, and I just want to point this out. We're going to, I think it's on the next page. Oh, there it is. We're going to need the moment of inertia for angular momentum. So I know that was probably a bit boring for you, but we are going to use this over and over and over again. So you've got to be excellent at it so that you're just not wasting time. Oh, how do I get I again? It's not that hard, but it's not that easy. You got to practice. And we have a special guest speaker here tonight, Phil.
Oh, yeah.
Hey, Phil, what can you tell them about chapter 10, chapter 11, the rest of the semester? Phil had me a couple semesters ago or something and got an A in this class, right?
Yeah, that's right.
What can you warn them about for chapter 10 and 11 in 1 minute?
It's hard. I mean, that's it. I got really nothing. All I did was do the homework as much as I could, looked over as many problems as I could, and tried them out until I got frustrated with them, and then went and talked to you, basically, or someone in my classmate. That's it. That's the key to this class.
Am I an asshole in office hours, or am I a nice guy, Phil?
No, the office hours are the best part.
Yeah. So use those office hours. I mean, I know it's hard. You've been on Zoom all day. Trust me, I know. I don't want to be there either, but I can usually be pretty helpful. That's why he's not in my class and he's still coming. So that says it all, as well as Ryan, who just showed up. So definitely, yeah. What can you say about? Hey, Ryan, I'm putting you on the spot. Can you hear me, Ryan?
Yeah, now I can. Sorry, I just connected to the audio.
No, that's cool. Didn't you get an A in 161 as well?
Yeah.
Okay, so they're doing chapter 10 and chapter 11.
Good luck.
What can you tell them about practice tests? Do you think the practice tests help you?
Oh my gosh. Yeah. I mean,
And
when
you had to take my
there,
class online, right? You had to do half of my class online, didn't you? Both
half of 161 online. Yeah.
Yeah, both of us.
So how did you guys prepare for the final, or how did you know that you felt comfortable for the final, or did you not feel comfortable?
There's always a little you never really feel fully prepared. But yeah, just doing as many practice tests as possible. I would say follow along with solutions as you need it, and do that to the point where you can start doing practice tests and not need the solutions. Go through them and do them on your own. Get to that point.
So use the solutions as much as you have to for the homework, but then don't use them for the practice test so that you can get the real feelings of crap, I don't know anything, right?
Yeah. And even if you're like, oh, you kind of like, quote unquote, cheating on the practice test, looking at the solutions when you need, you're like, oh, what is this? It's on the tip of my tongue. Following along with that a little bit, even with the practice test, but there's enough where you can do a few more after that without looking at any solutions.
Yeah.
If you can predict the solutions, you're good, basically. If you're able to look at it, you just know, okay, it's going to use these formulas, and that's what the solution is going to say. You're probably okay.
If you've done enough homework that you just look at it from your experience, you're like, oh, I've seen one like this. I kind of know how this one goes. I don't know the exact numbers I'm plugging in, but I know the formulas I'm going to use. Is that what you're saying, Phil?
Yeah, basically.
All right.
I think you mentioned even problem analyzation, I guess. Just break down the problem into what you know it's going to be. And then you know the concepts, you can just apply it as such. And then there you go. I got you. And then one last question. These guys got to get to a math class. I'm sorry I'm going on and on, but you had to take an oral exam with me. What was your feelings going into the oral exam? Did it freak you out? And then after you took it, what was your feelings about it? Let's start with Ryan.
Okay. Yeah. The very first oral exam we did, when it was like, hey, let's try to implement this, it was like, oh, how's it going to go? I'm kind of nervous. It was weird. Surprisingly, during the oral exam, I was calmed down a lot. It was pretty chill. It was like a good interview should go, like just it's a chill conversation. And if you think through it and say out loud your reasoning behind the things you say, and work through it verbally, it goes pretty well.
And you made some mistakes, right, during the oral.
Yeah,
But
and
I
I
would
mean,
try to say, oh, what do you think about this? Now that I tell you this, how would you? Oh, yeah, right.
yeah, and I could make mistakes and then say, wait. Now that I think about this factor, I think this instead. You know.
Yeah, a lot of times I just sit there and wait for you to make the obvious mistake, and then you'd be like, huh, and I'll wait for you to self-correct. And then if you don't self-correct, I'll try to give you a hint. Phil, any comments from you?
Almost the same thing. I mean, it was nice going over the test. You could see your mistakes and be like, oh, I can explain why I made this mistake. Like maybe you had a jip in your reasoning, and then you can go back and explain that, and it'll make more sense, as to why you made that mistake. Something like that. It's just nice to be able to explain yourself.
Yeah.
Overall.
All right, I'm going to stop the live stream and get to office hours. Thanks everybody for sticking around. And hey, let's give Ryan and Phil a thumbs up for me putting them on the spot there. Hey, there you go, guys. Yeah. All right, thanks. Now you guys are that